So how does LunyScript work? Game scripting across engines, portable code, it seems impossible, right? Let's go over the Looney architecture because it's really rather straightforward. Looney is an engine on engines, just like this shipping ships. LunyScript focuses on enabling game logic. It's the glue between the editor and your code. Behold the architecture diagram. It's divided into a portable layer and a native layer. And the goal is, of course, to keep the native layer as thin as possible because we might have in future more than two engines. Looney hooks itself into the engine at a single point of entry with a single native script, a so-called lifecycle adapter. And that's all that it needs. Start, update, shut down. Just from these updates, the Looney engine does everything internally, because it's so much easier to have a uniform behavior if you write that behavior yourself. Looney Engine also has so-called engine services, which are API entry points. So you get assets, input, camera, transform, animation, and so forth. And built on top of the Looney Engine, which handles the objects it controls inside the engine, is LunyScript. LunyScript then runs the state machines, behavior trees, so just sequences of blocks that it executes. LunyScript itself is a framework that sits on the Looney engine. The engine itself is a developer SDK for other users as well. This would open up an ecosystem of tools, services, where you can write code is going to work across engines. With an open ecosystem, there will be more services being added, maybe even custom services, maybe even engine-specific extensions. All of that is possible. And of course, we have a lot of engines that could theoretically run LunyScript. In the long term, I wish to add Lua to the mix. Lua would help to support other engines, also brings the ability to add game modding. So you script your game with Lua and LunyScript, and those scripts ship with your game and can be modified. And that has an interesting consequence because those modders modding games become engine scripters because they already know LunyScript. They have a head start in getting into game engine development or game development in general. This is my long-term perspective. Now let's look at Looney Engine. How is it going to drive everything? So this is the iLooney engine interface. It's an early version, of course, so it doesn't have everything. You will have access to services, to objects that Looney engine manages. Then you have observers and services. There are services that are required. Like every engine needs to provide some level of application interface, debug interface, editor, scene, time interface. Let's take a quick look at the native adapter that Looney Engine uses to hook into the lifecycle of the engine. The Looney Engine Godot adapter in this case, Unity has its own as well. This calls initialize, and it's instantiated by an autoload singleton, where I made a plugin script which installs this thing automatically. You just need to enable the plugin, that's it. Once it initializes, it simply creates an instance of the Looney engine. Next thing you know, Godot will call ready, which we'll use as our on startup. In Unity, it's the same. If we call start, we also send on startup to the Looney engine. So the native adapter gives us the startup, update, and shutdown methods, process and physics process, and we can also emulate late update in Godot, which doesn't have that. And we also handle crash and close requests. So in Unity, that would be on application quit. And when that happens, we shut down and destroy. So what about the Looney engine parts? Internally, it has a service registry where it finds all implemented services by scanning the assembly as basically reflection to find interfaces of a specific type. Then it initializes the profiler, the observer registry. The object registry just holds references to the objects that we manage. And the lifecycle manager is here to make sure that the objects come into existence, turn visibility on and off, and get destroyed. And all of this happens in a deterministic manner. For instance, we don't destroy objects right away because that just causes problems. Like in every engine, we have this problem. What we do is we flag the object as destroyed. And when that frame is over, that's when we actually destroy the object natively. That gives us way more control and way more reliability when working with objects. Let's take a closer look at the service registry. It just scans all the assemblies and gives us these service types. Once we have the checks done, we just store it in our service. The observer registry functions quite similar. We've just seen that code basically. We create an instance, we put it in the dictionary, and also when it's enabled, we add it to the enabled observers because we can also disable observers. The iLooney engine observer itself is practically an engine interface. Give me the engine startup, the pre-update, fixed stepping, physics update, update, late update, post-update, which means end of frame, and when the engine shuts down. And of course, some extra events that most observers would like to listen to, like scene loaded, unloaded, etc., just gets passed on to you. If you implement it, you'll receive it. So it's basically, I want what the engine is having, right? Yeah. What is the object registry? Like we have native objects, which we wrap into a iLooney object interface. When we register a engine object, we just put it in an array by its native ID, which is the engine provided ID, and the Looney ID is separate from that. So we can look up in both directions. So we have also the lifecycle manager. So when we activate an object, we also need to run a ready event at a certain point in time. That's going to happen before the frames update in the pre-frame update. So we need to have a queue of new objects that came in and then activate them in the next frame. And that's what this does. And similarly, if a user in the middle of a frame wants to destroy an object, we keep that in a pending destroy list, or queue rather, and just destroy it at the end of the frame to ensure we don't just pull the rug under the foot of the object. Now let's have a look at the API services. These are our native engine interfaces to things like input, physics, collision camera, and so forth. All services inherit from Looney Engine Service Base. A service might want to have an initialize, startup, shutdown, updates, and so forth. This has to do with the fact that in some engines, you don't get scene events, for instance. So you may have to poll every update to notice that change. That's why services also get these update methods. The services themselves are pretty thin adapters. This is the iLooney application service interface right now and just gives you is editor is playing and a quit method. The actual implementation for Godot here, for quit, we need to do some extra steps because we want to play nice and post a close request when we quit. Most of the services are actually ultra thin, effectively just passing whatever the engine is offering and giving it a different name or doing a simple conversion. Some services are a bit thicker than others, like the scene and asset services. They currently still are below 100 lines of code, but I expect them to have a couple hundred lines of code. So these are not gigantic monsters. They just need to look up by name, by type, and so forth. A quick look at the asset service. I've done this for the prototype, but it's not currently implemented. Most engines have slightly different paths, so we encapsulate that like the Looney object. We have a Looney path, which maps to a string. It does all the necessary conversions and the cleanup, like it cuts off this res stuff from Godot because we don't need it. We also have diagnostics. This is where the asset service also helps because it will return a not found placeholder. We don't work with null assets. So if you want to play an audio file and you made a mistake typing in that name, what happens is that the audio file won't just be not playing. You will get something like pip or missing or something like that. The same with objects. If you load a prefab and you make a typo and it doesn't find that prefab, it will just load in maybe a pink cube or something like that. This is done so you can go in the scene, see that pink cube, click on it, inspect it, and you get the error information, spells out your problem. We also have on-screen variables, so you can see what the state is of an object on the screen. Let's take a look at observers. Specifically, I want to look at the LunyScript runner, which is an iLooney engine observer. Effectively, it just calls run on a list of runnables, just call execute on a common interface. The LunyScript engine is just the public API, and this currently just provides access to global variables. Next, we have a list of script definitions, effectively just an ID for a script, its type, and its name. The script context provides us with execution context. We need, for instance, the script type. We have a Looney object that we reference, that we act upon. We have the global variables and the local variables. These are per object. We also have a couple internal references, debug hooks, block profiler, and most importantly, the scheduler, which is the most important part because it contains whatever event the script defines that it wants to run something on. So in the next step, in the event handler, we'll see it being used. The context has a scheduler that allows us to get a scheduled number of runnables for a specific event. So here we get the onDestroy runnables, check if they are not null, and if they are not null, we run them when the onDestroy event happens for that object. When that happens, since onDestroy is special, we unregister everything, we unregister the subscriber, the context, and so forth. So let's look at the Looney object proxy. This is actually part of the Looney engine. It's not LunyScript directly. A Looney object has the regular expected events, create, destroy, ready, enable, disable. It carries a Looney object ID and then also the native engine ID. We also have a reference to native object, the name, whether it's valid, that means it's non-null, it's in the scene, and so forth. So the Looney object runs the create, destroy events, and just have a look at this because we send them internally. Once a Looney object is registered, we activate it. This sends the created event. Since we call this after creation of the object, there's time to hook up that create event. When we destroy an object, proxy destroy, that's not the actual native destroy. We just check if it's already destroyed. Later we flag it as being destroyed. The lifecycle manager takes care of adding that object into the pending destroy list. So we have all these native events sidelined, which means we can also add various events that engines normally don't support, like pause, resume, show, hide, whatever we wish. This might come in the future. The Looney object is also upwards of 80% portable code. This is all in the Looney object native code. This is the implementation on the Unity side. The Looney Unity game object, it's just a mapping. We want to know if the object is valid, we just check it for null. We want to get the object's name, we get the name, and so forth. We have some assumptions here, so it's safe to call go name because it won't go null, because internally we always check if it's valid before we do that. For Godot, the same thing happens, except it's a bit more code because of Godot's object-oriented node hierarchy. So we need to do some type checking because there are no interfaces being used. Effectively, it's just the same. Call something, return something, done. The cool thing about a proxy object is we manage to destroy the state so that we can also do cool stuff like if it's no longer valid, we print some string where we just don't say, okay, there was an object here, it's just null, we have no information on that anymore. Looney has that information, at least in debug builds, we can print its former name and also the native object ID. So if something goes missing, we can still print what it was. Super important. Let's talk a bit about world design. There's one thing that most developers told me early on, that it's practically impossible to make engines interoperable because they're so very different. The core part here is the differences that you see in the UI. Godot has its scene tree, Unity has its scene hierarchy, Unreal has its world outliner. So it's completely different. Also, the native types are very different. Yeah, Godot has nodes, Unity has game objects, Unreal has actors. So how do you make them interoperable? Well, the first realization is, of course, all of the content that gets laid out in those engines is a tree structure. That makes it all the same, right? Except when you look closer, you notice that a tree in Godot is pretty deep and dense. There's more nodes than in any Unity or in a comparable Unity or Unreal scene. That's because Unity has a tree that has lists of things, and Unreal even has a tree that has trees in trees. It gets complex. So is that a problem for us? Well, no, it's not, because it's OOP 101. We can actually consider a node as a component, It doesn't have components, it is a component. So in that sense, all engines have components. So that's the same, except minor difference. At every point in the tree, Godot has an object with one component, and Unity and Unreal have objects with multiple components. The difference in reality with that is really just tree traversal. That's it. You just need to look at the tree in a different way and interpret it in different ways. So in Godot, when I want to get a component, what I actually do is I step into that tree that I'm working with right here with that Looney object and find a node of a given type. Not a component of a given type, a node of a given type. And that's the main difference. And actually, that's not really a difference at all. Okay, I would like to ask you to like the video, subscribe, leave a star on the GitHub repo for sure, and share it with friends or leave a comment. I probably didn't answer every question here, so put them down in the comments and I'll answer them. Thank you for watching.